So, so I will also be the main chair. So very quickly, so I'm at the Chinese University of Hong Kong, Shenzhen School of Data Science. If I have a few minutes at the end, I might say a little bit about that institution, just to give it a bit of advertising. So what I'm going to speak on is some work, relatively recent work with Elsiddig, who was here, maybe he's just got lunch, who's my PhD student still at KAUST. And it's work from partially observed McKean-Vlasov SDEs. I haven't given this talk before. I was supposed to give it in SUSTech, and then unfortunately my host got sick. Okay, so a brief summary of what we're going to be talking about in this presentation. So essentially, just to say a little bit about the context of the work that we've done, and basically the big picture of this presentation, followed by the main details on stochastic modeling. So this is really kind of the filtering problem, which if you don't know what it is, even from yesterday's posters, I'll try and tell you what it is, and then how it is we go along to try and deal with the type of class of problems what we're going to deal with. And finally, a summary of the contributions that we made from the theoretical and numerical perspective. So again, so the big picture, so I want to present some work which is on the archive. It should be submitted anytime soon on filtering of partially observed diffusions. So the idea is you have a discrete time observation process, stock returns, speech data, whatever you like, at regular intervals. They need not be regular, but so this is just for notation. And then underlying that process is a stochastic continuous time process, which happens to be McKean-Vlasov stochastic differential equation. And what I'm going to do is to show you some methodology to be able to filter such models. That is to say, as data arrives sequentially in time, what is the conditional distribution of the position of that diffusion process given the observation sequence up to that time. And the main contribution, what am I doing here? Yeah, the main contribution, I'll put this just easier. So the main contribution is here, which is a new multi-level particle filter, which is essentially a kind of variance reduction scheme, which is reducing the computational cost to achieve a mean square error. And of course, I will make that totally clear as this presentation moves on. And as I said, that's during work with Elsiddig, and now he's here, so you can enjoy some sort of exposition as a result of this talk. So, as I say, what is interesting or new for me is that it's a new type of particle filter. And again, if you don't know what a particle filter is, I'm hoping that I will tell you. I haven't looked at these slides for 3 weeks, so I hope I'm going to tell you. And it needs some kind of ingenuity, which was actually already in the literature for approximating expectations with respect to laws of McKean-Vlasov SDEs. And essentially, that's what we'll be doing, and it'll be clear again for the experts in the field. You probably figured out exactly what we are doing already. And that essentially facilitates the filtering of these diffusions, where the error of approximation doesn't increase exponentially over time, time being a kind of important variable in filtering. And then, of course, what is this multi-level method, and how can we apply it, and what does it do, and what is the point at the end? Okay, so as I say, it requires not only some new algorithms, but some non-trivial analysis, which I didn't do very much about that for once, so I let my student do that. But I'll give you the big picture of how that was done, and then if you want the details, you can look at the paper, you can ask Elsiddig, who's on hand in the audience. And we'll provide, and now what I'm going to do is give you the background information on what it is, what we've been doing. Okay, so we take, for some of you in this audience, is exactly the notation you have been using. A stochastic differential equation. So you have essentially a process in time. So the t subscript is time. You have a process xt, which is in r to the power d. And I'll assume that the initial point is known, only for simplicity. And then what you have is you have what looks like a normal standard deviation stochastic differential equation, which is driven by Brownian motion, except inside the coefficients are essentially expectations with respect to the law. This is a bit easier for me. The law of this SDE. So mu t denotes the law at time t of the SDE. And then inside these coefficients are these functions xij, where j is in set 1 to 2, j is 1 for the drift and 2 for the diffusion coefficient. And then you have some functions xij, so that's xi bar, this is xij. So these are expectations with respect to the law of this process. Okay, and this type of process it arrives in a wide variety of real applications, some of which I don't have to explain to you, but I think it's even become even more important because now the link between solution of nonlinear PDEs and McKean-Vlasov equations, SDEs, has become rather popular. There's been a lot of work by Roenecker and his group in Germany on that. So there's a lot of work linking PDEs and SDEs, or this particular type of class of SDEs. So I think not only are they interesting mathematically, they're also going to have some more applications in the future. Okay, so from a kind of statistical point of view now, we assume that this process is really of interest, and I've tried to explain to you why exactly that may be. And what we're going to do, the problem at hand, is what we have now is we have the observation process. So these are data Y, which are, again, some real valued observations are in the dy dimensional line. We see these at integer time points. They don't have to be integers, they don't have to be regular. I just don't like to put lots of notation in a talk or even in my papers. So they can be, we have done several works where these are regular time, but essentially the distance in terms of time should be some sort of order 1 point. Okay, so these are not really for continuous time observations, although the extension is relatively straightforward. Okay, and so we see those Y's, we know them, they're coming to us in real time, and underlying or driving these data process is this XT, this process we just talked about a few moments ago. Okay, so what we want to do essentially is to obtain the distribution of the position of this thing XT, given all the Y's, Y1 up to Y capital T, say, for capital T growing online. Okay, the conditional distribution thereof. Okay, so the notation here, epsilon T is a sequence of IID zero mean process. It doesn't have to be zero mean. Essentially, what I'm trying to do here, this is all over the place. What I'm trying to do here is essentially say that there's a density for the data, maybe Lebesgue seems to be the one we're using today. And what we want to do is again, in words, to estimate the conditional distribution of XT and functionals, therefore, expectations of, therefore, at each of the observation times. So I want to do that sequentially in time. So I have time 1, what's the conditional expectation of X1? At time 2, what's the conditional expectation of X2? So on and so forth. And as I said, there are a wide variety of real applications, and I think that those are going to grow. Okay, so that's why, one of the reasons why we started to look at it, I'd seen this work of Roenecker, and I got very excited that not many people were doing the kind of data versions of these models. Of course, many of you in this audience have worked on related problems, but not exactly this one. Okay, so what we're going to do is, the simple notation here is over a unit time point, we have the conditional density, conditional probability measure of the position of the diffusion at time xt, given that I know the law at time t-1 and the position of the diffusion. So it's essentially, if you think of it, this is a kind of Markov chain where basically I have a kind of input of the measure, and if you give me the measure at time t-1 and you give me the position xt-1, then that's enough for me to try and simulate forward the rest of the process, okay, in theory. And then what we say is that the density function of yt given xt has this notation g xt yt, okay, so that's just the density of the observation. So if I integrate over all possible y's, I'll get back 1 for any fixed point xt, okay? And so what we're trying to do in this problem, very simply, as you can see in the displayed equation at the bottom of this slide, is to compute, or would like to compute exactly for a class of functionals var phi, or phi if you like, of xt, the expectation recursively in time. So that says I want to do that in time as 1, 2, 3, 4, and as long as we want to do that problem in practice, okay? And this is the functional integral form, if you like, of the filtering distribution. Looks right, just right to me. Here where x naught is known, and if you want, you can put an initial distribution on x naught if you like. There's no problem with that. And so here, that's what I'm saying here, that the initial distribution is Dirac on the point that you know, initial distribution of the diffusion process. Okay, and so this is a difficult problem for many reasons. Before I go forward, so even if you don't have a continuous time problem, even if you have a discrete time problem, you can pretty much write it like this is essentially a discrete time problem at this stage, just to say. And the thing would be that this is typically numerically intractable, right? I cannot get an exact quantification of this thing, even in very regular filtering problems, i.e. where you have many, you've heard of the Kalman filter, so the Kalman filter you can, but any variance of that, generally, or nonlinear variance, there's no way to get an exact calculation of this quantity, and at high dimensions it's even more difficult, okay? So that's without McKean-Vlasov, that's without SDEs. But it's even more complicated for this problem, because in many cases of practical interest, the law of the process mu-t, I don't know it, and I don't know anything typically about even simulating this. So forget about the probability measure. Simulation of that is typically difficult. In fact, it's so difficult, as you're going to see in a minute, that even when you do time discretization, which is exactly what we're going to do, you still cannot simulate from that. It's a very, very complicated problem, which is one of the reasons we start to work on it. In fact, I find it so interesting. Okay, so I'm living basically in the world where this thing is essentially a mystery to me, and I want to try and still approximate numerically this type of quantity recursively in time. Okay, and by the way, the dimension here, you say D is the dimension of X, that's going to be moderate. I can't go over 10 with the methodology I'm going to describe. Okay, so what we're going to do first of all, in the first step to try and make this problem numerically tractable, is to work now with the time discretization of essentially the process xt, and by essentially proxy this dynamics P for the hidden diffusion process. Okay, so what I'd like to do is essentially to follow this nice literature which was developed in applied mathematics more than 15 years ago on multilevel Monte Carlo. Of course, not the first people to do that, but I like this thing. So what I'm going to do is I'm going to, in between each data point, break up the continuous time process over a regular grid. Okay, I'm not going to do anything fancy with grids or discretizations, because already the problem with these regular grids and these standard discretization are already difficult for me. Okay, so I'm just going to take a spacing delta L 2 to the minus L. And so the idea, of course, is if I send L to infinity, then I go from a grid to essentially a continuum. Okay, and so then I will work with an approximation of this thing, which will have some superscript L, and that basically this approximation of this quantity, if I send L to infinity, I'll get the exact thing. Okay. Okay, and again, I'm not doing anything fancy. In fact, I think this is a very interesting thing to do, is to work on discretizations of this type of processes and high order discretizations. But we take basically the simplest thing that we could ever have done, which is the simplest thing I could have ever done, which is Euler-Maruyama method associated to 1. So basically what I'm going to say is I'm going to discretize the process, and I'm going to use this notation mu-TL, let's just finally get the dot there, mu-TL, as being the approximation of the law of the McKean-Vlasov process at time t, where t is on my grid and has the superscript L, because L will be essentially defining the quality of the approximation with respect to the time discretized grid. Okay, and so in the equations you can see this is essentially your typical Euler scheme that you get for these things. And the first thing obviously to notice is okay, I cannot typically even simulate this. Okay, so normally when you work with the Euler-Maruyama method or any nice simple time-stepping method that we use in the statistical parts or applications of diffusion processes, you can easily simulate the nice discretization, even if you use some nice higher order methods, for example. But here you cannot do that. And the problem is perhaps not so obvious, but I'm just going to point it out, is because again, even though this thing on the end, this is a nice increment of Brownian motion, simple to simulate. The problem here is that inside these coefficients, we have these expectations, again, with respect to laws which I do not know, okay? And that's critical. So even though I've done time discretization, I still have something that I can't simulate, and that's important for the kind of methodologies which we're going to focus upon in this talk. Okay, but still we start to say, okay, now what I'm going to do is I'm going to say, okay, now there should be an L on this mu, but this is essentially the discretization of the transition dynamics. And as I made the point, you can't even simply simulate that. Nonetheless, my objective in this work is now, okay, I can't get the continuous time thing. Well, you might be able to, but that's not part of this particular talk. But what I'm going to do is I'm going to try and approximate now the filter at each of my observation times, but I'm going to pay the cost of a bias because essentially the bias from time discretization is all I can do, right? I have no way that I know of to get exact simulation, and I'm using simulation-based methods in this talk, from the dynamics of the McKean.
AJ,
yes.
Just quick question. If you go back to Euler-Maruyama,
yes,
you say that you approximate the law, right?
Correct.
So how do you approximate the law?
That's what I'm going to tell you.
Okay.
Exactly. Yeah.
Yeah.
Thank you. So as pointed out, the problem here is still very complicated because, again, all the numerical methods which are classical in this literature typically require at least the ability to simulate these dynamics. And these dynamics are difficult to simulate because, in fact, they're indeed intractable. Okay, so that's the problem I want to do. I want to compute the filter. I've discretized the filter in continuous time. And now I say, okay, I want to now still do that problem. And of course, I will have pay a bias from doing Euler-Maruyama, but that's life, okay? And now the question is, how can I do this scheme, even due to the fact that the transition dynamics of the McKean-Vlasov, discretized McKean-Vlasov scheme cannot be simulated, okay? And as pointed out just a few moments ago, we have to consider a method that can actually approximate mu-TL. That's clearly critical because if I can't approximate this thing, then this thing is a dead duck if I want to do the exact thing, right? I'm living in the world where I believe in the model and I want to do things exactly, and I'm prepared to pay the cost of doing so. Okay, so let's suppose we're given a time t, and the approximation of this thing is classical in the literature for SDEs, McKean-Vlasov SDEs, which is this very classical paper back in, I think, 1991 of Schnitzman, and it looks very complicated, but the idea is it's in what's called an interacting particle method. Okay, so I'd spend a little bit of time saying a little bit about this thing. Let's say, yeah, there's a lot of notation here, sorry, but what's the idea in broad strokes, okay? So the idea, suppose I start at the beginning of time zero, okay? So the law at time zero, I know there's no problem, is Dirac mass on the initial point, okay? And I'm going to produce n samples, all x0. Okay, so essentially I have capital N copies of the initial point of the diffusion process. What is this? Oh yeah, sorry, I went ahead, yeah, okay. So that's what I'm going to do. Sorry, I'd already got to the particle filter, excuse me. Okay, so the approximation at time zero is just the Dirac mass on x0. Okay, this is what this thing says. So I haven't done anything complicated. Of course, this is not my idea either. So then the idea is then for each particle, I'm going to increment. So here I increment, I get the next point on my grid, and that's the old point in my grid for the particle I, the superscript is I. So this one says that time delta L, I'm the old point at time zero, which is x0. And now what I need to do is some small things. The first part is easy. I generate my Gaussian increment. This is my Brownian motion. So this is just a Gaussian random variable in d dimensions with zero mean and variance covariance matrix delta L times the identity. So nothing complicated here. And now what I'm going to do is I'm going to plug inside the coefficients the approximation of the law at the previous time point. So at time zero, of course, that's just this Dirac mass. And when I plug in these points, what I have is just these sums. Okay, so this is an order n sum. So this is basically an approximation of those integrals which are inside the coefficients of my McKean-Vlasov SDE. Okay, so I know how to compute this. So for example, this point here for a given j is just my previous time points, and then I have to compute this for each xt minus 1 ki. Okay, and I'm going the right way. Okay, so essentially what I'm doing is I'm saying the approximation I got at the last point on the grid is plugged in to the coefficients, and that gives me my new point on the grid. Okay, and this by the way, so that means just roughly, because I'm plugging in essentially these type of empirical measures, okay, for each sample that I simulate, I'm simulating n samples. It costs me order capital N to simulate one sample. So this is a capital order n square algorithm. Okay, and essentially this one can be simulated, and it's a very well-known algorithm. Okay, and the key point here is that it's been analyzed, it's been discussed. People know this thing very well, And essentially if I'm going from time 0 to time 1, say, I can get the approximation of the laws from time delta L to time 1 using this procedure. So essentially, there are a lot of equations, but the key point is this is just regular Euler-Maruyama, except I'm using capital N samples to approximate the drift and diffusion coefficients using Monte Carlo. Okay, that's I think that's the easiest way that I can say that. Okay, and as I said, this is not my algorithm; it's well known. Okay, now why did I tell you that? Because essentially, I'm going to use that inside the particle filter. And in fact, what happened is when we worked on this, developed the idea, this methodology, this was the only way that we could work out how to do the approximation. So so what I explained in the previous couple of slides was a way to approximate the laws of the McKean-Vlasov SDE up to a numerical approximation, and of course the bias on the time discretization. And now what we're going to do is we're going to use that method to develop a particle filter. So this is step 2. Okay, and it's new. It's kind of new. I don't know. I didn't see anyone use this method before, but maybe it's fairly obvious for people who've worked on this thing before. So I'll give this algorithm up to a terminal time t, but it doesn't have to be the case. So this is an algorithm to do exact problem interest. Okay, it's to my knowledge new. So at the beginning, so now what we're going to have is we're going to have several degrees of approximation. So L, don't forget that. That's how precise or how fine, sorry, my time discretization grid is. So if I send L to infinity, of course, I have a very expensive algorithm, but I have an algorithm which is very precise with respect to the bias of the time discretization parameter. I have N. N, capital N, is a number of samples that I use for my particle filter. Okay, and that's a Monte Carlo approximation of the expectation of with respect to the functions with respect to the unknown diffusion. And M, that's going to be the number of particles that I used in this method of Schnitzman. Okay, so here I'm using N, but this method that I was just talking about, I'm going to use capital M samples there. So there are several sources that occur in the algorithm I'm going to present, but the key point is if I send all of those parameters to infinity, I'm going to get an exact approximation of the filter, and that's what was basically my objective. Okay, so essentially what you do have to do. So the first things first. Okay, I don't know the laws, so I'm going from time t equals 0 to t equal 1. Okay, so I run that method that I just talked about from time equals 0 to time equal 1, and I bank, if you like, all of the approximations on the grid. All right, so this is an exponential method in terms of the size. It's going to cost you 2 to the power L to do that, but I have nothing else, so I can't do anything else about. I can't do anything about that. Okay, and now what I have is that what I'm going to do now is I'm going to simulate the dynamics, plugging in exactly the approximations that I get. So everything I'm doing in step 2, it doesn't depend on my particle filter, right? So I'm plugging in the approximations, and it's critical. In fact, I don't know another way to do this method. If you do it a different way, you get in a bit of trouble, as we find out when we try to do this problem. So here what I'm doing here is I'm running the Euler-Maruyama method, except in the approximation of these coefficients, these approximations are coming from this kind of independent process. Of course, this one here is depending on this one here, but the key point is that this one is run independently and is approximating the law of the McKean-Vlasov SDE.
So this is just the step before you put the data in.
Exactly.
At this moment, everything is parallelizable. There is no data.
Perfect. Yes, exactly that. Yes. So now what we are going to do is exactly put the data. So what we have to do is a typical method in McKean, in the particle filters, sorry, for each of these capital N samples in my particle filter, I'm going to compute an approximation of the filter, which is essentially I plug in the position of the McKean-Vlasov SDE at time t, where t is 1 in my example, and I compute what are the normalized weights, okay? And now using this quantity VTI, which are called normalized weights, I have now an approximation of my filtering distribution. So I have 3 levels of sources of approximation: L, the time discretization, N, the number of particles, and M, the quality of approximation of those laws. And basically, this is just a weighted sum. That's all this thing is, and it is completely computable, and I can do that very, very easily. Okay, and so then what do I do? Now, the key point here is that I can't keep on doing, so some of you might say, okay, well, I could just stop here, now I can loop back, right? I've got my position, And now I can get my new laws, I can get my new positions of my particles, and I can try and do this again. But this is the key point in particle filters is very well known. I can't do that very well. Otherwise, I'm going to get a source of error with respect to this time parameter t, which is going to grow exponentially in time, right? It may still be exponentially in time, so it's not typically the case, but I have one way to try and mitigate that, and this is the well-known resampling method in particle filters. So essentially what I do is for each of the capital N samples, I pick one of these N samples as an index J sub superscript I, that's a pointed one to N, and I pick that index according to this, which is a probability mass function, because these weights G are strictly positive by assumption. They're probability density functions. Okay, and then, so essentially, if you don't know what I'm talking about, you have T, capital M positions of the diffusion, time T, and I basically pick one out, take it out, put it back in, do that capital N times, and that gives me a new set of samples. And essentially what you're doing is you're replicating those samples which are most consistent with the filter. Okay.
AJ,
yes.
Just to follow.
Sure.
N was the number of particles inside of the system.
Of the particle filter.
Was the number of replications of the system.
Capital M is the number of to make the laws of the McKean. Capital N are the number of particles which are designed to approximate the filter.
So N is the classical, and M is the McKean-Vlasov.
Exactly.
Okay,
exactly.
And you resample in N. Yeah.
Capital, yes, exactly. Yes, yes. There's no resampling. Those are frozen. Yes, yes, yes. Yeah, this is a J. Yes, sorry, this is a J. Yes, there's something from J is 1 to N, and this is a J. Yes, that's a typo. Yes, thank you. Okay, and so what this will do, so you can keep on going from time as 1 to capital T, if you like, or you can keep on going for as long as you want, essentially. And this will give you an approximation for any class of, any collection of functions for which it makes sense. Just so long as you can evaluate the function of interest, you can do exactly the scheme of okay, and this is expensive. It's going to cost you the number of points on the grid. That's 2 to the power L. The m squared, that comes from the McKean-Vlasov approximation, and the m times n comes from the simulation. So you have to do n samples, and each sample costs you m because you have to use your laws that you've been approximating inside your simulation. Okay, and as I was asked very nicely, and as I to elaborate here, in step 2, it's absolutely critical that what you're using to approximate those McKean-Vlasov laws is run in its own world, right? It gives you information, but you're just doing that as if you want to, just to approximate the laws. Otherwise, this was the first idea that we thought about, where you just use the resampling with the laws, you get into a total mess and you actually get the wrong approximation. So this nice idea of feeding in the approximation, which has been used, of course, by Raoul and his co-authors, and of course by Dos Rice, used to be at Edinburgh, I think it's at King's College now. That idea that we had read, it was critical here. Without that, you would be in trouble. And so essentially the error with respect to the time parameter, so this is the cost per observation time. Okay, so you can put a little t here, and that's how much it's going to cost me just to do this. And that tells you nothing about how well you want to do your approximations with respect to the mean square error. Okay, and so as I say, the error with respect to the time parameter number of data points, it should be controlled, and it can be uniform in time, but you're going to have to do a lot of deep analysis in terms of stability. That SDE typically would have to be ergodic, or at least have some nice stability conditions for that to be the case. And that may not be the case for any method that I know of that's been used. I don't know of any method that's been used for this problem, but maybe somebody who does, and he can tell me about it. Okay, and so just a couple of remarks before we go ahead to the main meat and the contribution of this work. So improved discretization methods can be used. In fact, I think that there are several higher order methods you can use, and that will make things better as we move forward in terms of strong and weak errors. But again, I just wanted to give you the simplest thing that we could think of at the beginning. And we can show, in fact, we will show that if you fix L, so L, you've got to fix L at some point, because you can't, at some point the computers can only take a certain value of L before it says I can't do any more work. But if you allow capital N and capital M to go to infinity, we have not only in fact convergence probability, but almost sure convergence. So this thing will give you an exact approximation, and the rates we will discuss as we move on in terms of N and M, and in fact, the bias according to L will be discussed as we go forward. Okay, and then to obtain a mean square error. So what's the mean square error? So I take this thing, that's the truth in terms of discretization. I take that away from this, I add it on again, and I take away the true expectation, and I take the square. Let's suppose we're in dimension 1. Okay, so the mean square error is the average squared difference between my numerical approximation and the true filter with no time discretization bias. And if you work through the calculations, I think we'll show you something later on in the talk if I have time, to obtain a mean square error of order epsilon squared, I should say, not epsilon, per time step, that's going to cost you epsilon minus 5. Okay, and to be honest, I don't know that you can do anything better with this type of method. It's Monte Carlo. You can already see for those of you who are specialists, you know that capital N, that has to be epsilon minus 2, capital M has to be epsilon minus 2. And the bias of this is a certain order, typically of the Euler-Maruyama rate, and you're done. That's it. So the remainder of this work is then, if you still believe in the world where you want to get exactly the true filter, can we do a little better than that? And that's what the remainder of this talk is going to be about. And I have about 20 minutes, so I'm watching the time, don't worry. Okay, so that's what I'm going to try and do. And this is a kind of work that I've been involved in for a while, and I think this was probably one of the last kind of models that we probably look at before we start to do something else, but still I think it was interesting this time out. So we want to reduce the cost to achieve that mean square error. Okay, I want to do better than epsilon minus 5. Okay, and we'll show how this particle filter can be extended using the context of multilevel Monte Carlo. And this is a new multi-level particle filter, MLPF, Mark's called multi-level particle filter. Okay, and so again, very quick crash course on multi-level Monte Carlo. I know probably everybody knows this business off by heart, but just to show you, what we're trying to do now is, instead of having one approximation, time discretized approximation, I'm going to have capital L of them. Okay, so I can start from 0 if you like, or you can start from some lower bound L bar. But anyway, so we have this clear telescoping sum representation of the time discretized filter. Okay, so T is going to move, but the L's are going to be fixed. And the idea is to approximate the right-hand side of this identity. So in brief details, what is the method that we're going to do? So in this lowest rank approximation, what I'm going to do is run the particle filter method that I've just discussed, right? That's all I can do. And then the idea at subsequent levels L, which is again denoting the quality of approximation in terms of the time discretization, I'm going to come up with a method to approximate this difference such that I essentially have a particle filter that's doing the job here, a particle filter that's doing a job here, and I'm going to correlate the two so that I can essentially get a variance reduction to approximate this difference, and I'm going to do that independently for each summand. Okay, that's essentially the idea. Okay, and now of course there are the details, which is the devil of this is the details, and of course the analysis thereof, because the algorithm is fairly well understood by now. And so, as I say, it's trivial looking telescoping sum, and it can be leveraged into a variance reduction method. So if you don't know this method, you could maybe think about control variance. It's not exactly that, but it's something related. And that variance reduction is the idea there is to reduce the cost to achieve the mean square. That's all I'm trying to do here, nothing more. And so essentially what I'm going to do, as I say, is to approximate the right-hand side of the previous identity. So again, just to review what I said, the first term is the particle filter. That's the method I talked about already. And now I'm going to say, how do I do this for each summand? Okay, and it's important. So of course, before I say anything, and if you don't know these methodologies, the obvious answer might be I run a particle filter here. I know run a particle filter here independently, but that doesn't going to work well. There's no correlation between those two numerical approximations, and it's critically the correlation between those numerical approximations which precisely allows one to achieve the variance reduction which we're seeking to do in this type of work. Okay, that's exactly what I said. You see, I didn't read the slides. That's why but at least I know what I'm talking about, apparently. So the key is basically to couple the two particle filters using what's called a coupled particle filter. And essentially, we have done that before. For example, Kengo Kamatani sitting in this audience, we had done exactly that work for regular SDEs. And now we want to do that for these McKean-Vlasov. And of course, it's not that difficult. So essentially, the critical difference is that you don't know the law of the SDE. And so that's the extra contribution we make. So essentially, it's how to do multi-level particle filter with SDE. With unknown laws. And the other thing, of course, here is then how do you do the analysis? And that's the two tricky parts of this work. And so if you don't know this work, what I'm trying to say is essentially in words what it is. I'll give you the details. You may get bored. I mean, I've been talking for 40 minutes. You may get bored with what I'm saying. But this is the idea in a nutshell. And then if you get the details, that's great. And if you don't, you can please read the paper or we can talk afterwards. So the CPF, which is the coupled particle filter, essentially is the idea of running two particle filters and correlating sampling and resampling. Resampling is, there's nothing new to do here. We have done that. That's not just work that Kengo and I did with Cody Law, but also Eric. We did work with that on a separate work, which we did. So that's more or less, we know what is almost the best thing to do, but it's correlating the sampling, which is the work, and of course, the stochastic analysis. And so, as I say, the correlation must be done sufficiently well so the second moment of this centered approximation falls sufficiently fast with L. If that sounds cryptic, I'm afraid I can't make that sound any easier than it is, but I'll at least show you the results, and then it may perhaps be clearer as we move forward. Okay, and listen, this is in words, because I think we'll give the algorithms. Yeah, I'll give the algorithms, but I don't think you're going to get a lot of that in a short period of time. So in the sampling stage, this can be done very simply using what's called strong error results for SDEs with synchronous coupling. What does that mean? Well, what it means is this. So let me just try and say the following. So let me just give you the point. So essentially the idea is what I'm trying to do is I'm trying to run Euler-Maruyama dynamics here at level L, and then I want to do another one at level L minus 1. So these are my n samples here. I have another set of n samples. Okay, so if I imagine that I know how to calculate these coefficients, so forget about McKean-Vlasov, that's very easy to do in such a way such that I get exact samples from Euler-Maruyama at level L and exact samples of Euler-Maruyama at level L minus 1. And the difference between them is very small as a function of capital L. And that's essentially by using the synchronous coupling. So I simulate this Gaussian random variable at level L, and I do that twice, because at level L, I have 2 points in the grid, and level L minus 1, I have 1 point. So I do my two simulations of these. If I add them together, I have exactly the sample of the noise at level L minus 1. That's what's called the synchronous coupling. Okay, and so of course now the critical point is that we don't have this problem. We don't only have this problem, we also have the fact we have the laws, and we have to do some work there. Yes. Sure. Yes. Please.
Sorry, in the equation that you, under the previous one, where you have all the particles, the n particles.
Okay.
No, yes, this one.
Yes.
So mu m is frozen from the previous approximation.
Yes.
Right. But how? So you have two sets of particles, those for evolving the McKean-Vlasov, the measure, and those for the filtering. And they evolve from time 0 up to time n.
Yes.
Parallel.
Yes. Yes, exactly. Yes. Is that clear? Thank you. Thank you. Thank you for the question. Yeah, sorry, maybe it's not clear. Sorry about that. Yeah.
Was it clear which two sets of particles you were using? I thought that it was like a set of m capital repetitions, and each of them corresponds to one system of McKean-Vlasov.
So yeah, you have capital M samples. You have that. So the Schnitzman method is running in the background, and so when you go from time t minus 1 to time t, the McKean-Vlasov method is fed in, and you do your particle filtering work. Then you go to the next time point. McKean-Vlasov moves on.
Yeah, the problem is not with the times; it's just with the one single time.
So in
all data.
Yeah, so you run the McKean-Vlasov approximation from that
using n
capital M.
n particles.
Yeah, okay. And then using those laws, you run the system of the one you're going to use in the particle filter with those approximations inside it.
increasing the law.
Exactly, yeah. So at each time, so if your time, let's say this time in the grid half, you use the approximation of the grid of the McKean-Vlasov at point half minus delta L. So it's fed in.
So then you're using the decoupling method. That
Exactly the decoupling.
Okay,
exactly.
That was not so clear. So
okay.
you use the measure, right?
Yes.
And it give conditional on this measure. Each of the particles evolves independently, and it is a standard SDE.
Exactly. It's exactly that method. Yeah. Sorry, I'm sorry. I thought it was clear, but
That's a crucial step.
Yeah. Yes. So where was I? So now what I want to do, or I want to say, but lost my. Yes. Okay. So where we go back. I'm going the wrong way. Okay, yes, this is here. So, so what I want to do now is to basically couple that McKean-Vlasov driving method, and it's essentially the same thing. The Brownian motions that you use at level L are the Brownian motions concatenated from the one you used at level L minus one of the ones you used at level L. And so this is what it looks like in equation form. Yeah, that's it. So this first slide, it looks like a lot of work. It's essentially this driving method that we were just discussing a moment ago. So you have here capital N, I keep on keeping N and M, but this is just the McKean, this is the Snitsman method, okay? That's level L. The critical point is now what I'm going to do is at level L minus one, and I'm doing essentially the same thing, but these Brownian motions that I'm using here, these are the ones that I used at level L. But that's essentially, you can think of it like that. Okay, and this is these are just the details, okay? And essentially that gives you an approximation of the laws on the grid granularity delta L, and approximations of the laws of the grid granularity level L minus one, delta L minus one, but they're correlated, okay? That's the key point here, okay? And so then finally the method of, so the final method is this, okay? So imagine it's all it is. I have capital N samples, I'm approximating the filter at level L minus one. I have capital N samples at level L minus one. And I'm approximating those, and those cloud particles are going to be dependent, okay? And marginally, as if I did my particle filter method at level L, and marginally it's going to be as if I did my particle filter at level L minus one, but they're correlated, okay? And so this is what it says. So I have at the beginning all the two particles are the same, okay? So then I do my correlated approximation of the laws, and then I do coupled Euler, which is what I just said a moment ago. So coupled Euler is essentially using the Brownian dynamics. And now I have my weights at level L, I have my weights at level L minus one, and I can approximate the differences, okay? And so the critical point is these things here, they are very close as I allow the level L to go up. In fact, they should be very, very close together, okay? And so that's how you correlate the sampling. To correlate the resampling, we use the method of maximal coupling. You can also use the method of Wasserstein, which we did with Eric and Raoul some years back. Okay, so there's a way to correlate the resampling mechanism. I don't get into the details. Okay, so the method is simply this. Okay, I'm aware of the time, so don't worry, you don't have to push me along. So we run the particle filter with N0 samples and M0 samples. So N0 is the approximation of the particle filter. M0 is the method for approximating the McKean-Vlasov. And then independently for each of the levels, 1 to capital L, I run this coupled particle filter, NL samples for the particle filter, ML samples for approximating the law. Yes.
Are you coupling also the McKean-Vlasov?
Yes. So I'm sorry, I didn't make that clear. I went over that, but yes, exactly. Yes, that's critical. Yes. So the estimator that we have, essentially, we have the approximations in the particle filter. I showed you what that looked like. That's just a weighted sum. And this is just a difference of weighted sums. Okay, so I can compute everything. There's no problem. And the computational cost of doing this per time step is the finest time grid, the cost of doing the McKean-Vlasov approximation, and the cost of inputting the McKean-Vlasov into the particle filter. Okay. And now the question is, can we minimize this computational cost to achieve a given mean square error? And of course, that's the key point. So what I want to do, so I have my estimator here, I have my approximation here. I suppose this is 1D, so I square it and I take the average, okay, over the randomness in the particle filter. And what we want to do then is to show a meaningful bound as a function of capital L, the number of samples at each level for the particle filter and the number of samples used at each level for the McKean-Vlasov approximation. And so how to do that? So I'm just going to give you, of course, I'm not going to write the proof simply because it takes too long. But the idea is essentially this, is what you do is you add and subtract a fake, so-called fake estimator. So the fake estimator is the one where you did a coupled particle filter, except you didn't have to approximate McKean-Vlasov. Okay, so you say, okay, I have my estimator. I take away the fake estimator, which is as if I didn't have to do McKean-Vlasov. I add it on again, and that fake estimator has been very well analyzed already because that's just Euler-Mariana. Okay, so that's the idea here. So the error between the fake estimator and the true filter, as we've already done that. Okay, because you're just doing Euler-Mariana, you know the laws, so called. And the main challenge is actually to consider the error between the estimator we use and that so-called fake estimator. Okay, so under assumptions, roughly, actually, there's a missing term in this thing, but roughly the mean square error looks a bit like this. Okay, in fact, I think you've got a capital L in here actually, but that's not so important. And so we prove roughly this is the order of the mean square error, and then what you can do is you can try to find the values of the number of samples, NL, the number of McKean-Vlasov samples, ML, and the overall level of discretization bias to minimize the cost for a given mean square error. And so it turns out that the calculation of computation we get is either this one, and actually get epsilon -4 precisely, although we don't have the proof of that yet in other scenarios. So you're basically reducing by log factors. If you're doing this method, the best you're going ever to do is epsilon -4, because you have two sources of Monte Carlo error. So this is that to achieve these mean square errors. Okay, very good. So let's have a look at quickly some numerical results, and we'll finish. So we have a very simple stochastic Kuramato model. I think this is what everybody is doing. So we have constant diffusion coefficient. So there's no McKean-Vlasov law here. And the observations are Gaussian random variables. I don't know the details of this. I didn't do that. And this is just a simple plot, just a cost against mean square error. So essentially what this means is as you reduce the error, the cost goes up. It's a kind of log-log scale. And so what we're doing is you should get a -2.5 for the single level, and you should get -2 for the multilevel. So this is the optimal case, which we didn't have a proof for, which is why I didn't say that. But that's essentially the numerical results we got. I don't know the number of data points here because to say anything there. Okay, and that's very interesting. So that's essentially all that I wanted to say on that. Before I finish, I know that I'll just indulge me just for one more minute. So as you may know, as at the beginning of the talk, I'm going to make you sit through me doing all this. I am now currently located at the School of Data Science at the Chinese University of Hong Kong, Shenzhen. So we have several faculty positions in statistics, operations, research, and computer science. So if you have some interest, if you feel like you want to move somewhere, please send me an email. I'm here until the end of Thursday, so please send me an email. We can talk. I can describe to you the place, and if you have some interest to move here, please let me know. That's all I wanted to say, and thank you so much for your time. Sorry, I'm the chair. Does anyone have any questions?
Hi, thanks again for a very nice talk. So I assume to get the complexity that you have, you assume some sort of convergence of the convergence rate of the McKean-Vlasov law to the empirical law, right? Is this something? Yeah. So what is this? Is this the usual 1 by square root of p, or is it like 1 by number of particles, or?
No, I think so. The McKean-Vlasov analysis, I think it's order 1 over m or something like that in terms of variance. So we don't assume it. I think there are already results that are in the literature. In fact, you probably know them better than I do. So yes.
Okay. So, but that would come at the cost of some assumptions on the regularity of the.
Absolutely.
Yeah.
You can't escape that. Yeah. So if you don't have those regularity conditions, this doesn't hold. And this is the case. You can go to the ordinary SDE case. And if you don't have a nice elliptic SDE and so on, then this stuff doesn't do anything.
Okay.
Exactly.
Okay. All right. Thanks.
So if you're running a multi-level, so you choose N and M together. So I guess a natural question is, could you decouple and go to multi-index?
Sure. Yes. Absolutely. Yes. And that's your speciality. So you probably could do that better than me. But yeah, absolutely, you could do that. Yeah.
Yeah.
Just curious, how important is to take mean square error here? Can you use other functionals?
Yeah, absolutely. Yes. You can use things if you don't have moments, and you can work with the probability or something like that. Those are different. This is one metric because we are working a very regular problem with bounded functions, and there's no problem. But if you have to go to weaker type of things, then you absolutely could do that. Yeah.
Yeah. So next question. Connected to the final error versus work, right?
Yes. Please ask a question. I'll try and get there as soon as I can.
No worries. So you got essentially epsilon to the -4.
Pretty much, yes.
For work.
Yes.
Right, and to get that's the square of the error essentially to be epsilon to the
Squared. Yes.
square, right?
Yes.
So standard error will be epsilon. So do you believe that there's room for improvement there?
Yeah, you could probably do a bit better with better discretization methods or better coupling methods and stuff like that. I don't know that you can do too much better because you have those two. You have to approximate the law, and once you approximate the law, you have a kind of m squared. So if you have a better way to approximate the law, or if you have a better way to couple the particles, I think you could do a bit better maybe. But I don't think there's too much better.
So you get this complexity epsilon to the -5 or epsilon to the -4.
Yes.
Because I guess you're assuming a full coupling between the particles. So
yes.
You have some sparse. So the m square cost comes from the particle system.
Yes, that's good. Yeah, so the m squared is from the McKean-Vlasov and then once you do Monte Carlo inside, then yeah.
Particle efficacy.
Yes. Yeah. There may be some. You're going for the most basic thing you could think of, which is what we're doing here. You're not doing better than that. But if you start to kind of tweak with couplings and other techniques, maybe you can do better, but not this one. So I think that's probably it. You don't have to thank me again. We have 5 minutes, and Arnold Jensen will be speaking in 5 minutes. Thanks.